Hi, this is Chris Mangelsdorf. If you're hearing this, it's a pre-recorded version of my presentation because I didn't have the bandwidth I thought I did. One of the worst things that can happen to a project is to encounter some sort of analog problem. Analog problems are very subtle, and analog blocks, ADCs in particular, are very complex. They're very high performance these days, but they have a lot of moving parts. Um, the analog problems are particularly troublesome because we can no longer probe the way we used to do with the older technologies. And the performance of the circuits is dominated by parasitics, which don't appear in the original schematics and have to be extracted from the layout. Now, these extractions are notoriously tricky, and so you're often getting the wrong answer, or you don't get the answer that you really need. And finally, the traditional tests really are good for speccing the performance or checking the overall performance that the customer will see, but they are not good for revealing what's wrong with the ADC. So what we need is some creative solution problem solving. Traditionally, this problem is dumped on the lap of the product engineering group. But that isn't really fair because they don't have, in many cases, don't have the resources or the experience to deal with this. And it really should be a multi-group, interdisciplinary problem, including not only product engineering, but the test group, who has a lot of different resources and experience and techniques. Also, the design group are the people who know what the weaknesses of the ADC are, or how the ADC operates, and how it's liable to respond to different kinds of unorthodox tests. Now, this is not designed for testability. DFT prepares you for what you expect. This is more what I like to think of as test for disaster, TFD. We're testing for things that you didn't expect. This is the problems you didn't imagine when the design was being put together. And what's required is something that's simple and immediate, because this is most likely holding up the project and you need to get answers quickly. It also needs to be creative because the normal pathways that you use for testing the product are not going to reveal it, most likely, or you wouldn't have gotten to this stage of panic. And finally, like I said before, it needs to be interdisciplinary because a lot of brainstorming has to go on here. Okay, this is our outline. I'm going to show you a few examples right now. Some are what I call the free tests. They don't require any preparation at all. You can do those very easily and quickly. Some are almost free in that they require a change to the test hardware, the test board, but not to the silicon itself. And then there's this third group where you really have to go in and change the silicon. And so this last one is very expensive and very time consuming, so you want to avoid it. Now, I only have 15 minutes, so I'm going to be going through these fairly quickly. But the important thing here is that you get the feeling of the kind of out of the box thinking that you need to get answers about what's going on inside the ADC and not be locked into conventional methods. Then finally, at the end, I want to present two things that I think are useful items to have on the silicon, which give you a lot of flexibility later if you should need to debug the ADC. One of the things that often goes wrong, but which is very easy to test for, is called kickback. And kickback is caused by the sampling action at the front of the ADC. And most ADCs have something like this structure in the front, with the exception of, say, continuous time sigma delta, which don't do this. But it often looks like this, where you're charging a capacitor with the input, and then you open the switch to hold that input so the ADC can convert it. The problem happens when you reconnect the switch to take the next sample. Now, in that time, the input may have changed, and so there's a pulse of current that goes through the switch as the sample capacitor here takes on the new value. Also, sometimes these capacitors are reset in that they're shorted between samples, so that each time you take a new sample, you are actually having to completely recharge the capacitor. So depending on the structure, this can be signal dependent or not. But the problem is that it rattles through the whole input network of the A to D. Now, it is related to the sampling rate. So one of the things you could check very quickly is to just change the sample rate and see if that affects your performance. It may be signal dependent, so you need to keep that in mind. You know, for example, if you're putting in DC into a signal like this, there will be no kickback because the capacitor is already charged to the previous value. One of the quickest thing to do is just to change the cable. Particularly if you're working with the cheap cables, you can get a lot of reflections bouncing back and forth in there. The next easy thing you can do is just plug the input, replace the signal source with the oscilloscope and see what is being kicked out. This is assuming that the DC value at the scope will be appropriate. And finally, a more elaborate technique that you can use is represented by this article down here, where the authors actually were correlating this kickback effect with the sampled value and able to numerically tune it out. So that's a very interesting approach that you can use as well. If I were shipwrecked on a desert island and could only choose two instruments to have with me, the first, of course, would be an oscilloscope, but the second would be a time domain reflectometer. These things are highly useful for diagnosing any kind of transmission line effect. They tell you a lot of things, they tell you it in great detail, and they tell you it instantly. But surprisingly enough, this is a tool that's alien to many analog folks, particularly converter folks, because they're usually not that involved with any kind of transmission line. So this is one of the first things you can do, and it's very nice because it shows you quickly, as you can see on the screen, it shows you the impedance of the line as a function of distance along the transmission line, and you can pick out all kinds of features, and you can debug what's at your input. Is this capacitance? Is your strip line on the test board mismatched? It just tells you a lot of stuff. So it's a very quick and very helpful way to check what you've got. And it's probably a good idea to use even if you don't have problems, because you want to check that your input signal path is clean and without a lot of reflections. Okay, when it comes to looking inside the silicon to look at how the ADC is performing, the spectral performance, this spurious free dynamic range in particular, are very important in all kinds of signal processing these days. And so it's important to check the harmonics. But what people usually don't do is they do not check how the harmonics behave versus input frequency. And if they do, they almost never check the phase, which is interesting because the phase carries a lot of information about what is causing the harmonic distortion. For example, if you have a fixed, what we call static distortion mechanism, like just plain nonlinearity, like a limiting factor, you saturate the amplifier, and the distortion that you get with that has the same phase independent of the frequency, because the distortion mechanism has nothing to do with that. So that's a big thing right there. And you can see in this picture that's not the case with this particular one. This shows the performance. This polar diagram is showing the performance of one of the harmonics versus the fundamental input frequency. And you can see that at low frequencies it's fairly low, and it's about 180 degrees out of phase with the fundamental, and then it starts to increase, but it also goes through kind of a resonance here between 5 and 6 gigahertz, where the phase shifts nearly 180 degrees. And so this kind of a diagram, for example, or just any kind of analysis of how the harmonics behave versus frequency is very important. Now remember that this phase is usually kind of an arbitrary thing in most FFT outputs, because you didn't synchronize the input signal with the sampling window. So you need to calculate the phase relative to the fundamental in each capture record that you do. And also don't forget the filter effect. That is that further down the signal chain, after this distortion is created, these harmonics are created, they are necessarily limited by the bandwidth or roll-off that you have in the signal chain after that point. So what you're looking at in terms of amplitude and phase could be related to the mechanism, but you have to also be sure that it's not related to just the signal path that follows the distortion source. Our last item under the free tests is some time domain tricks that you can use to look at the waveform in what I think are very useful ways. Unscrambling the waveform, for example, to look at a single cycle of it in great detail. I'm not going to spend any time here because I suspect that many of you already know these tricks. I learned them myself from a test guru at Teradyne. If you want to see more, that I wrote it up on an article for the Solid State Circuits magazine, which is referenced here. Now here's a trick that will most likely require some modification to your test board, so it's not completely free. But the essence of this test takes advantage of the fact that modern ADCs are almost always differential beasts. And because of the low voltages inside, you can't really construct a truly differential input stage, a buffer or sample and hold or whatever's going on up here. So the signal path going to the ADC probably has circuitry which is what we call pseudo differential. It is the same on both sides, but it's not strictly differential. It's two parallel paths that are carrying signals kind of opposite phase, basically. So one of the useful things that you can do to diagnose this is look at just the performance of one channel by itself. In other words, in this picture here, you ground the lower channel, and then the upper channel gets some signal. Now, in order to do this, you have to check with the design folks to see if the ADC can really tolerate that. Because in fact, when you drive a differential input with a single-ended source, you get a lot of common mode. And depending on the architecture of the input stage, that can be devastating. So this will not work with all ADCs, but I have used it for some. And when you do, it's quite powerful. And what you do over here says there are actually two tests. First of all, if you're testing for the nth harmonic, let's say you want to test, say, the third harmonic, and your input signal is at, say, 1 gigahertz, then the third harmonic would be 3 gigahertz. So you put in a very small signal here at 3 gigahertz, and you measure the performance of the ADC at that frequency. And that really tells you how this chain propagates that signal to the output, because you're going to be looking at the output of the ADC or something related to it to see the performance. Okay, so that means, so what it's saying is, you know, if I put in that small signal, is it going to be filtered or blocked or anything like that? Then you put in the original frequency, say 1 gigahertz, at a large signal, so that it actually creates a distortion harmonic at 3 gigahertz. And now you can know when you measure the output at 3 gigahertz to look at that distortion, you'll know if it was at all corrupted or changed by the bandwidth of the channel. So those two tests together enable you to kind of figure out how each side responds to the input harmonics. And in the case of even harmonics, they should cancel out. So that gives you, if they're not being canceled out, that probably means there's a mismatch between the two sides somehow. This shows an example of doing that test that shows you how the harmonics change with the input frequency here. And you can see along the horizontal axis is the input frequency, and then the vertical and into the screen axis are the polar coordinates of the harmonic itself. And you can see that at low frequencies, of course, both harmonics are very small and very, very, very similar, but at higher frequencies, they become more and more different. And this is very useful for you to know. Okay, here's another trick. Usually, modern A to D converters have some sort of calibration on them, and usually the designers put some mechanism for turning that on and off, so that you can diagnose, how is the converter doing before the calibration and how is it doing afterwards, and are there any artifacts associated with either state. So that usually happens automatically. But one of the other things that we don't think of very often, because it is so old, is this idea of digital, what we used to call digital error correction. And this is shown in the block diagram here. This is a pipeline ADC, but there's a similar kind of effect used for successive approximation converters, where you take first you take a coarse sample, then you take a fine sample, and you combine the two together to get your digital output. And one of the things that you do is that you put extra range. Well, you can think of it in either way, but you put extra range into the second stage here, so that it can correct for errors in the first stage, or kind of misestimations made by the first stage. So the second stage range is bigger than it needs to be, and so but that automatically corrects for a lot of different errors. Well, these days, that correction range is used for all kinds of things: sampling errors, slewing problems, even distortion. So that the extra range that you have in the second stage is not necessarily just fixing comparator errors in the first stage. And sometimes you want to know how much the errors are contributing. And so it's nice to look at this performance without that correction working. And so, if you build in a way to turn that off, you can sweep the input and see things that tell you what the uncorrected performance of the first stage is. And that can reveal things. For example, if you have auto-calibrated comparators in the A to D at the front, and that's not working correctly, that will show up immediately here. So this is something that you can use. It's not generally too hard to incorporate in the ADC, but we don't normally think about it because this is has been such a fundamental part of ADC structure since time immemorial. So anyway, if you'd like to read more about that, you can find it in this reference here. Finally, to wrap up, I'd like to introduce two things that I think are useful additions to any ADC embedded in your system. The first item is some sort of decimator, which takes the data from your ADC and essentially drops most of the sample. So it effectively drops the sample rate that's passed on to the digital system that follows the ADC. It drops that sample rate while the ADC is still working at full speed. Okay, so this allows you to test, to isolate, in many cases, the performance of the ADC from the performance of whatever follows it. Now, in high-speed ADCs, if you have to go off chip with the ADC data, you have to use something like a SerDes, like JESD 204. And so that has its own problems, and it may not be reliable. It in itself is a very complex and delicate analog system. So you may want to figure out where the problem's coming from your digital transmission or from the ADC itself. And so this allows you to isolate the two. The other thing is that the error rate of the JESD may be comparable to that of the ADC, so that you can't test the error rate of the ADC by itself without decimating the data first. So this is useful for that. Now, in many systems, you may not actually have access to the raw ADC data. It may be processed on chip some way. Excuse me. And if you don't have that, it's very useful to provide a set of low-speed outputs, digital outputs, so that you can look at the A to D. But for many high-performance ADDs, they want to clock at a much higher rate than you can really take on with a very low sample rate output. So this dividing the clock rate down, doing this decimating, basically gives you a way to do that. So that's good for all kinds of things. If the JESD isn't working, if you don't have access to the data in the first place, if you want to do bit error rate testing, again, you want to eliminate any error rate associated with the JESD. And another important thing is the real-time output, and I'll talk about that in a minute later. So that's one way to use that. But having an additional set of outputs may not be an option because it takes a lot of pins. Another thing you can do, for example, is decimate the data and then pass it to a DAC to create an analog signal. So you basically reconstruct whatever the A to D is doing. Now it's much easier to create a slow high performance DAC than it is to create one that works at the same speed as your ADC. So this, again, decimating the data allows you to get a real-time output and diagnose ADC without having to rely on the digital output if it's flaky or just not available. I'll show you an example why that's important. And then finally, a lot of times you're looking for some kind of glitch. And for example, in bit error rate testing and things like that, the glitch detector, which is very easy to build, also makes a good addition. I can show you that in a second. For me, the biggest benefit of the decimator is the fact that you can get kind of real-time output from the thing. Modern evaluation systems where you have to go through serializer and then the high-speed interface, they have a lot of latency there, but then it goes off the chip and often off the board, then to some sort of PC, and you look at the data in the PC, and then you can put together, you can calculate a spectrum for it, So there's a big delay between you taking a measurement, capturing some data, and actually looking at it, and that can actually slow you down because there are a lot of things that you just want to try real quick and see what happens to the signal. For example, I believe that the most important test tool that we have is our fingers. You can check connections by just pushing on elements, for example, if they're not too hot or too high voltage. It's a socket problem. It's a weak connection, something like that. You flex the board a little bit, you'll find it. And this happens all the time, but you can't really see that unless you're pushing on it real-time. It's very hard to find. So having real-time output is very important. Another thing is the finger is a very good cap load. You can check, the effect of a little filtering or effect on stability by just touching the signal trace, given that it's low enough voltage, of course. And the finger is also a good signal injector. I'm sure I'm not the only one to debug audio equipment just by touching the contacts to see what 60 hertz sounds like on your system. And finally, it is your finger is a temperature system. And if something is warm that shouldn't be, you'll quickly know. And then the classic test where you take a heat gun, basically a hair dryer, and heat the board up real quick and see, what does that do? Does anything change? Does anything latch up? Does anything go away? Or you put on the freeze spray, so you instantly, but while you're doing this, you want to be looking at the output. You want to be looking at either the waveform or the spectrum or something to see what's happening. So you want the real-time output, and that's what the decimator gives you. The effect of the decimator is also that it aliases the waveform. Basically, you're subsampling the original data from the ADC and to a much lower sample rate. And so that aliases the waveform down to a different frequency, which can be very, very helpful when you're trying to diagnose things. For one thing, if you take a high-speed signal that's up near Nyquist or up beyond Nyquist and alias it down to a low frequency, you can actually see things about the signal you didn't notice before. But also, as we'll see, it helps with using the glitch detector. This is the glitch detector, and this is something that I would put on all silicon if I ran the zoo. It really is taking the derivative of the signal that's in the ADC data by subtracting a delayed sample from the current sample. And then what you do is you compare that to a threshold value and see if it's greater than or less than, and use that information to trigger a counter. This shows the example of the glitch detector at work. The first thing you should notice is that you want to set it up so that you alias the waveform down to a very low frequency. So the signal component doesn't really cause the output to change much from sample to sample. So you're aliasing almost down to DC. So the derivative that's in this decimated data is very, very low. And if everything's working right, the only deviation should be thermal noise. So when a glitch does come along, it stands out, and you can see that here it is where there's a difference in this sample here pops up that causes a kind of a doublet, which triggers the detector. And this allows you to see instantly if you've got a problem or not. And this can be useful for real time, but it's almost essential to do this for bit error rate testing, because there's no way that you could test the billions and trillions of samples required to find low, for example, low metastability errors and so forth. You can't do that any other way except at real time or almost real time with the case of this decimated data. So this is, I think, a very useful thing to have on your silicon. Okay, that brings me to the end. If you have some questions, you can reach me at this email address down here. If you can't spell Mangelsdorf, you can use this one here, my IEEE address. But thank you very much for your attention. Bye.